Good evening. So today is the fifth week of the our session, and I'll be covering today few of the detailed topics for the remote sensing in hydrology. So first, we will see the polarimetry. We will discuss about we'll discuss the about the sharp polarization property, how we utilize this in our hydrology and in other applications. Then I'll be discussing few texture features also. So till now we have seen that about the properties of the radar return and its properties of the radar return and its image signatures. So the energy reflected from the terrain to radar antenna is called the radar return. And we have seen already that these following parameters that strongly affect the radar return, that depends on, first is system properties, second is terrain properties. The system properties that we can't manipulate, terrain properties we can decide. So system properties include the wavelength or frequency, that is often we discuss, the polarization, and third is the incidence angle. So these three are the system properties that comes with the antenna properties. And this second one is the terrain properties. So terrain properties means the material, the target. So our target varies with the different material, size, shape. So that has the material property directly constant. In terms of shape, has surface roughness, feature orientation. So we will see how all these things affect our studies. And so we already know that the set of the radar wavelength bands, that starting from the K band and ending to P band, and in normally which band we use, and the how they are coded with the letters. So starting from the K band, that has very the lowest wavelength in centimeter, and as we go to the higher wavelength, that K, X band, C band, S, L, and P band. So in this session we will see or we'll work with the allows 2 data, that is L band, that varies from 15 to 30 centimeter wavelength, and also the C band data that we already see, that Sentinel 1 data, so that has 2.4 to 3.8 to 7.5 centimeter wavelengths. So the radar return, that depends on the wavelength, how we already have seen a few examples how it interacts, which one to use for which application. And the terrain features, that is our targets, that have a unique interaction in a particular wave band, and hence the return is also unique for the wave band used. So every one target, it varies or it returns the signal that varies from wavelength to wavelength. So shorter wave bands have atmospheric effects because of the interaction with the atmospheric water vapor, and longer wave bands that can penetrate to some extent our atmosphere. That has the minimal effect. So we'll see few examples in the image how it looks. So here you can see the expand image, expand VV image, the first one. And second one is the C band HV image. Final third one is the L band HV image. So here it is said that in the first one there is one impression due to rain. So heavy rain that has the, so expand, it caused the atmospheric effects. So that impression, the dark patch came due to the rain interference. That black cloud in X band, that is 3 centimeter image, faint in C band. So the same image that has C band, that is in higher wavelength, so it can now, the signal can penetrate through the clouds, or so now it does not have that much effect from the cloud. So the black patch is lesser here. And finally, the L band that has higher wavelength than both X and C. So here there is no impression due to the cloud. So we see no black patch here, and we can see the terrain totally different. It appears totally different as compared to C band and also X band. Here we can see in the L band that how so detailed features we can differentiate between many land targets here. So that is how the wavelength is so important, and it changes the same image in different wavelengths. And one thing also to notice that water that appears dark in all the images. Okay, this portion you can see in L band compared to C band, it it is more bright. But the water, that is, you can see one river that appears as dark for all the three images. Why that we will see today. So the choice of wavelength is very important in terms of our use or application, because the radar wavelength should be matched to the size of the surface feature that we use to discriminate. That is, if we work with ice discrimination, that is very small size, the feature of ice is very small, so we use X-band that has very low wavelength. And in geology mapping, that has comparatively large features, so use L band, and so on. Some these foliage penetration, and I mean it has different. So finally, what C band lies in between, and that's why we call C band is a good compromise over everything. Because I mean, not always you will get access to all the data, and the X band is mostly accessible to some sort of features, and P band is to security purpose because it has the highest wavelength. So C band lies in the middle of the scale. So it is a good compromise to use and to see in any application. Here you can see similarly the influence due to the wavelength. So it is a agriculture fields, mixture of crops and woodlands. Agriculture plots are there. So in expand how it appears, the color. Look at the color and contrast. That has a wavelength of 3.2 centimeter around. L band, it has very much higher wavelength, 23.5 centimeter, and how it appears. It appears this type because it can penetrate to some extent to the land surface. Very upper surface of the land, it can penetrate that to an extent of 2 to 3 centimeter. So it appears different. Both are same image, but here the L band is reading the target differently. So why? What it is reading in that on the target, that we will see. Here also another comparison just to show you that how the band and the wavelength matters. The C band how it looks, L band how it appears, and P band highest wavelength how it appears. So in the three bands, the received signal, through the received signal we can see different things. We can see things at different levels. C band can see the very much upper of the target. L band can penetrate to some extent, 2 to 3 centimeter of extent. So it can see that part of the level of our terrain, that features. Further, P band, it can see some other some more features in depth because it has the highest wavelength. So it is our interest of which of target we on which target we are interested. If we are interested to the for the lowest level, then okay. If the surface level, then another band. That's how it works. So choice of radar wavelength, system factors that high wavelength, and so there are limitations also. It is not like everything we will only work with the high, the longest wavelength. Okay, it has limitations also. So high wavelength that is difficult in processing, need larger antennas and feeds and simpler electronics, and low wavelength need more power and more difficult electronics and good component availability at expense. So many research SARs have multiple wavelength bands. So it can have multiple wavelength bands also. So air SAR, sensor, SAR C, these are multiple. So here comes the polarization. So we will discuss today one of the properties of SAR image, synthetic aperture radar image, that is polarization. It has one distinct property, and the study of this property is the polarimetry. And how it is useful, what is actually polarization, and how it is useful in our application. So as we see, we have seen this before also, the electromagnetic radiation waves, the sinusoidal waves, that has the one electric field and one perpendicular to that field, one magnetic field. So we call it one V polarization and one horizontal polarization, and it has one direction also. It is lying on a 3D space and it has direction. So because of that directional property, it is the polarization. Polarization without direction is nothing. So there can be four types of combination. Okay, these four combination you must know. What are these combination? What does it mean? So V signifies the vertical and H signifies the horizontal. So if you will read like VV, HH, VH, HV. So the first one is the received one, always remember. And the second one is the transmitted. So when we transmit the V, this type of signal, and we receive this similar line signal, then we call it VV. When that is HH, the same. When we transmit the H and receive this H, then it is HH. But when it is VH and HV, VH means we transmit the H, we transmit this type of oriented signal, and we receive this type of oriented signal, that is called VH. So this is the first step, we are entering into polarization. So what polarization refers to the orientation of the electric vector of an electromagnetic wave, and it is called the orientation. And radar system antennas can be configured to transmit and receive either horizontally or vertically polarized electromagnetic radiation. And when polarization of the transmitted and received wave is in the same direction, it is referred to as like polarized. So there is co-polarized and cross-polarized. So HH refers to the horizontally transmitted and received waves. That is called co-polarized. If we transmit the H and receive the same H, it is called co-polarized. And when we transmit the V and receive the H, that is called cross-polarized. So these are the nothing but the terms that we call. So when the radar wave interacts with the surface and is scattered from it, the polarization can be modified depending upon the properties of the surface. This modification affects the way the scene appears in polarimetry radar image, and the type of surface can often be deduced from the image. So what is actually the transmitted, what is actually the received signal? So this is the first one is the HHVV, like polarized or co-polarized image, and VH and HV are the cross-polarized image, we call it. So radar system containing single antenna can receive only one type of image, either of the like polarized or either of the cross-polarized. If radar system contains two antenna, it can receive two image types. simultaneously. That is either both like polarized or both cross polarized, or one like polarized and one cross polarized. It depends what is the antenna built. So a comparison of like and cross polarized returns might reveal darknesses differences leading to terrain identification. So water and trees appear same in like and cross polarized images, while swamps appear brighter in like polarized and darker in cross polarized imagery. Grasslands appear darker in light polarized image and brighter in cross polarized. So why these appear like this? That we will see. So choice of polarization. Basic or operational SARs usually have only one polarization for economy, that is HH or VV. So because it is not that heavy to do the mission, so either HH or VV, only one type of polarization it can receive. Research systems tend to have multiple polarization. Those are heavy, that has the all four types of polarization, that is called quad pole or full pole. All the possible polarization it consists, and it is very heavy, and these missions are costly. So these are always not open source, these are commercial. So multiple polarizations help to distinguish the physical structure of the scattering surface. So the alignment with respect to the radar, that is Hs versus Vv, the randomness of the scattering. So, mostly vegetation responds to this HV. Corner structures, that is the it changes the phase angle, HHVV. Bragg scattering, that are oceans, that is VV. So this is one, I mean, very generic implementation of how to differentiate between which band shows what. So we can see HH in HH how it looks, but the same area how it appears in HB polarization. It is different because in HH it it is sending or transmitting the H horizontally polarized wave and receiving the horizontally. So the orientation is not changing. Okay, and it is called, it is sensitive to the horizontal surfaces. Okay, if it gets vertically, then this will appear, because here V vertical is transmitting, but it is changing the orientation and we receive the horizontal. So here it is sensitive to vertical structures. So HV is when we want to suppose detect vertical structures, we will use this band HV. If we want to look for smooth, I mean, horizontal, that smooth surface that does not have any height on terrain, there HH is sensitive. Similarly here also how it looks, another in HH system it looks like this. In HV many of the, you can see the terrain, we selected the this kind of terrain, not flat, where you can see the difference. These are the mountains and these are the hilly areas. This appears how, so this is the one how we, I mean, mm, make the notation, how we see it. That RGB image, normally in our human eyes we can see the RGB image, we have to channelize the set channel to certain colors. So we, because the, because of the HH, VV and HB, we channel this HH band to red and this HV band to blue and VV band to green. Why? One thumb rule is this HH, it is sensitive to buildings. This VV sensitive to vegetation, so green. HV sensitive to water. So we got this RGB. Similarly, this kind of RGB image we can create in C band, how it looks in L band, and this HHL band. So we will skip that. So what is polarimetry? One thing to understand, it is so many things we will study, but it is nothing but a filter. Polarization, we are catching or capturing the polarization of certain features. So we are transmitting certain oriented signal, it is hitting the target and it is changing its characteristics. Then we are receiving back that signal. So now that received signal has the characteristics of the target. It has some change, it changed due to hitting the target. So that is that. Now with that received signal we will see that how much polarized. So you can see it that way, that it is a filter. When suppose you are transmitting H horizontal wave and you are receiving only horizontal, but it is giving you everything. It is giving you horizontal also, vertical also, but you are filtering out that only horizontal. That is how you get the HH band. Similarly, when you filter out the H but capture the V one, then you will get the HV. So you can visualize this as filter. Polarimetry or polarization is nothing but a filter. So with that, we need some notation or some form to process us to store those bands. We got the HH, HV, VH, VV, these four from the received signal. Then it is called, we are not going into very detail with this scattering matrix and this matrix. If anyone is interested, we can discuss in the next week, but today it is the starting and very basic. So I will be just telling you the covering the basics one. So by scattering matrix, stoichiometry and polarization signature can be computed for each pixel. So when it comes for image, polarization in image, how we visualize that or how we handle that. So it can be a powerful classification tool because it is giving you another parameter that is called the polarization. And till now in optical we use the spectral signatures, that is one feature. Here using SAR we can use the intensity also, single phase also, but the polarimetry, it is one of the quality of that data or image that we can separately use. Okay, so scattering matrix can be used to synthesize the return with any transmit or received polarization. So one thing to notice, to synthesize the return. So here again we are virtually or synthetically creating the return or received signal, okay, with any transmit or received polarization to investigate the scattering properties of different surfaces and to optimize polarization for optimum detectability. So basically it is the another plus of addition to the parameters, you can say, and it is different to other our remote sensing parameters because it is very much sensitive to certain characteristics of our target that others are not. So one chart to show you what are the broad domain and for which we use the bands, what kind of polarization normally. So for vegetation application and vegetation we use this type band. Our interest is in soil moisture or anything related to water. So we there use the C and L band. C is always, you can see common C everywhere because it is a good compromise and we have the open source data. But L band, because the surface, our surface, earth surface is covered with many types of land cover, land use land cover. So we need, and sometimes it is need to penetrate that surface to some extent, to a centimeter level. That L band can do. C band it cannot do. So by using L band, we can study the soil moisture or water surface on our earth in more detail. So now comes the incidence angle. Incidence angle we already studied, and we saw in geometry what is the incidence angle there, if anyone can recall. So it is the angle between the radar beam and a perpendicular to the surface. Okay, no need to remember that way geometrically. It is an angle that is very important. And how it is important? So rough surface produce relatively uniform radar return irrespective of the incidence angle, and smooth surface gives a stronger return at very high depression angles. Depression angle is another angle that we calculate, that is near vertical or low incidence angle, but little or no return occurs at lower depression angle. So how with incidence angle, I mean change in incidence angle, the surfaces change, but the thing is with one for every data you get, the incidence angle is fixed, but you have to know that what it ranges between and how it is different to other. Because suppose your C band data has certain incidence angle, but when you are using your L band data, it does not differ only the band, it differ with the incidence angle also. It has I mean other some other incidence angle, it can be higher lower to the C band. So the it depends on the incidence angle also. You can see the as the incidence angle decreases here from 58 degree for the first image, second one, and the third one. How it appears, it how it changes. The higher 58 degree is very higher incidence angle. Normally we don't work with this kind of higher incidence angle. How here the classes, how it appears. Open water is the this W that appears darker. C is the clear cut area in the forest. These all are not that much annotated. Clear cut areas. Swamp, power lines are there, road and forest. So you can see in this patch in 45-degree incidence angle, the water and the swamp land, it appears this. And in the lower incidence angle, okay, I will answer every after one slides. Okay, let me continue first. So how it looks, and that is why we many of us we study the how what are the effect on changing incidence angle. So we take different types of data of different incidence angles, and we study that, or we process that, then we try to draw inferences that okay, this type of application is working here, this type of application we can see this thing here. So that is one part of application. Now comes the most important, I can say, the dielectric constant. Polarimetry or polarization of a target is I mean it depends on the dielectric constant very much. Dielectric constant of the property, as I've said that polarization depends on the target material properties, its shape and size, and also orientation. So one thing we have seen that it's the shape and size. Next, the dielectric constant, its property, the material's property to store the energy. So the electrical properties of matter influence the interaction with electromagnetic energy and are called the complex dielectric constant. It is a complex. Okay, it has some real part, the dielectric constant numerically. It has one real part and one imaginary part. So dielectric constant can be stated as the ability of the material to get depolarized when electromagnetic field is applied. This material depolarization in turn is related with the amount of polarization of the interacting energy. That is, if the material has very high dielectric constant like water, water has the highest dielectric constant we know. it will depolarize the incident electromagnetic radiation better, and hence the intensity of the received signal will also be more, which gives rise to brighter tone. It should, the water should be brighter. Okay, but it is not in SAR image. Why that is, that we'll see. So dielectric constant for some of the materials in that we face in our image: water, dry rocks and soils, metals, vacuum. It has the this ranges. So water is has very high. Metal, we will see its application. So here, if we see this image, this is one SAR image, and it has the bridges, metal bridges, and this is the water. So we have seen already, we read that high, I mean dielectric constant, which has, I mean, which material has high dielectric constant, it should have the brighter, it should appear the brighter in SAR image. But water is not appear brighter, it appears darker. Why? If anyone wants to answer that, because it is one of the most important questions in SAR study. If anyone knows who wants to answer, you can. And similarly for metallic structure, it is, I mean, as per the rule, it appears the bright, because the it is the measure for conductivity closely related to water, that is dielectric constant. And dry matter has this, wet matter is this, and metal before we have seen 3 to 2 to 5 metal, and it is very high. So metal appears dark, brighter, because of one of the reason is that. So why the water, it appears dark in every SAR image? Before also we have seen the three different bands, where in every bands so many things were changing, but water was not changing. And in SAR image, water should appear as bright, at least bright or little bright, but everywhere it appears as dark. When it is mostly pure water, not much affected with atmosphere, any interference or any sedimentation, anything in between the water. Because water works that way, it has 80 around approx dielectric constant, it should appear brighter. But what happens, water has the smooth surface, very smooth compared to other terrain surface properties, terrain targets. So because of the polarization, here specular reflection happens. What is specular reflection? So when the transmitted signal hits and the received signal, it goes into one direction only. But if you recall the SAR, the antenna, it is moving from one point to another, towards the azimuth direction. So it misses that received signal, because it is not scattering the signal to everywhere. It is scattering or reflecting the signal, the transmitted signal, to only one direction, and that definitely the antenna misses. So that is why, because of the, it is, I mean, the smoothness of the water dominates the dielectric constant effect in water. So here the shape or the surface properties or the roughness that we'll study, what is mean by the surface roughness in the in polarimetry. So that is why the water appears dark. So here, because the specular reflection dominates the dielectric constant. So a measure of the material's electrical characteristics is the complex dielectric constant, defined as a measure of the ability of the material to conduct electricity. Dry surface material has this in microwave region, water approx 80 So most significant parameter influencing a material's directly constant is its moisture content. So when so in presence the presence of water, it is changing because water has so high reality constant compared to other. So it is influencing, and moist soils reflect more radar energy than dry soil. So in soil moisture detection studies, it is very important. Many use the polarimetric parameters because the when there is the soil particles have moisture or water droplets, it I mean it reflects, or its signature scattering or its signature is different compared to dry soil. So what we can do, we can differentiate using this soil, moist soil and dry soil, we can differentiate using this. So the amount of soil moisture influences how deep incident electromagnetic energy penetrates into the material. So what happens in soils with high moisture content, incident energy penetrates less and scatters more brighter return. So what we have seen, that dry soil is showing some reflection. When it has some moisture content, it it acts as, it gets some smooth surface of its particles. So now what we have seen in for the case of water, pure water, it has so much smoother surface. It shows the specular reflection. Here also that is happening. When the soils have moisture, the particles will get smoothen out. So that way it will not the signal will not penetrate that much. It will reflect. More the power, it will get reflected. So it will reflect more, so that will appear brighter. Now comes the another property, terrain property, that is surface roughness. So we have seen the material property, that is the reality constant, its electrical property, and another is the shape or size property, that is called as roughness or surface roughness property. So surfaces can be either smooth or rough or intermediate. Smooth surfaces reflect all the energy away from the antenna and will be resulted in dark tone. That happens for water. Rough surfaces diffusely scatter the energy equally in all directions, irrespective of the angle of incidence. So it will scatter in all directions, the transmitted signal. So what happens? The our antenna is moving, sensor is moving from one position to another. So it will get some part of the received signal. Okay. So intermediate surfaces scatter the energy diffusely but not equally, since a portion of energy is peculiarly reflected and the rest diffusely scattered. So which surface has intermediate roughness? We'll next slide we'll see what are the how we quantify the roughness. So which has the intermediate roughness, surface roughness, it scatters the energy diffusely. Diffuse scattering. It is scattering in every direction, all direction, but not equally, since a portion of energy is peculiarly reflected. But obviously, these are the natural targets. So naturally, it will not, I mean, reflect or scatter the uh, power, the same power in all the direction, like an ideal source. It will not. Because of that, a portion of energy because is peculiarly reflected and the rest diffusely scattered. So there are two phenomena is happening. Specular reflection also happening and diffuse reflection also happening. Now this is how we quantify surface roughness. This is very important of Rayleigh criterion, it is called. So it is the um, scientist who proposed these different scales, that Rayleigh criterion considers surface to be smooth. We will consider a surface to be smooth if h, that is height of the surface. Surface means to us height of the target, and that is very small, you can say. suppose the soil particles, and lambda, that is the radar wavelength, and gamma, that is the grazing angle, the angle between terrain slope and incident radar wave. In the previous slides, you can see the geometry there, all are mentioned. And it is smooth when the h, height of the surface, is less than lambda by 8 sine of gamma. This is the already in physics, this is given. We are using this property to assess the polarimetric response. And when it is rough, the our target, we consider it as a rough surface, rough target, when the h, height of our target, is greater than this. So the Rayleigh criterion defines the smooth, rough as well as intermediate surface when this lies this. So h, when h is greater than this and this to this, I mean h lies in between this part to this part, it is called intermediate surfaces. And other than water and mostly water surface, mostly our terrain, our targets lie in the intermediate surface. That's why it is very complex also. We have seen it shows both diffuse and specular, and what the antenna is receiving, that is also very much complex to differentiate. Now wind influence, surface roughness, that is also we have, I mean the can see in the river the smooth water surface causing low backscatter. Again the water is appearing here. Here you can see this is our sensor, which is moving for water surface. It is transmitting and the signal is going away from the sensor. That's how it is not getting any signal from the water. So it appears as dark because we are not getting any signal from there. So nothing to, I mean very low or zero value for that pixel, or dn value for this pixel. So the more the values, the brighter the pixel. And for here, these this is called, already I have told, the salt and pepper type of noise. This is noise because this texture is not a terrain property. It happens because of the rough water surface in the river, because many, I mean our weather is windy, and the water surface, water repels on windy, it can penetrate the atmosphere, but it has the effect on of the water surface, that is rippling because of the wind. So because of that, the texture coming, and it we consider this as noise. And because of that noise, I mean because of this roughness, diffuse scattering happening, we will get certain scattering, suppose, but this appears this salt and pepper, and this is a noise. We are not interested in the ripples of the water, okay? So this is a noise to our image. So surface roughness characteristics, it is a terrain property that strongly influences the strength of radar backscatter. And surface roughness may be interpreted as the micro, meso, or macro scale. And one may use the modified Rayleigh criteria to predict what the Earth's surface would look like in a radar image if the surface roughness characters and radar system parameters are known. That is also the backward simulation, you can say. This is how it is reacting. Relatively smoother surface, specular reflection is happening. Near perfect specular reflection. There is, I mean, our target, and when we get signal or data from one of area or earth surface, nothing is ideal, everything is natural target. So everything will be mixture of all the geometric properties, nothing is called the perfectly smooth. And the intermediate surface roughness, how it works, you can see the it lies between this height And when it is a totally rough surface, there how it is more diffused. The transmitted signal is more diffused here. Now the last one, and very it is also the polarization also differs very much. It depends on the feature orientation. How our target is oriented with respect to our signal, radar return you can say, or radar movement. So orientation of the linear features with respect to the loop direction affects the radar return. So the orientation with respect to what? Orientation with respect to azimuth direction. We measure it that way. Azimuth direction to the direction the flight of our sensor is moving. So if the feature is oriented perpendicular to the loop direction, then the identification of the same becomes possible since it gives strong return. And if the linear feature is oriented parallel to the loop direction, then identification of the same becomes very difficult because of the weak return and poor contrast with the neighboring features. So this is to understand perpendicular to the loop direction. You can say loop direction. So we are looking, suppose, so this is the terrain. We are looking from here this way, and in plan if we see, suppose in plan we are seeing, so it is looking in this direction. We are transmitting signal this direction and receiving signal this direction. Radar is moving this way because it is sidewise looking. Now the features that are perpendicular to the loop direction, so this direction perpendicular is the this direction. So the feature that lies like this, suppose on building, so it will hit this and it will get many response, and it will get the strong response from this target. But when this is parallel, suppose this any kind of this longer surface, how to know the parallel or perpendicular? The longer surface we will always see, the longer or wider surface, it is oriented. Here the wider surface is parallel to this direction. In this case, this type of orientation, it will get weak return. Why? Because here only it hits this part, this small part of the surface or building. For this, it is hitting this larger part, wider part of the building. Only because of that. So vegetation responds to our microwave energy. It is influenced by the following biophysical parameters: vegetation, that is canopy as water content. Now we know the polarization, when it hits the target, it gets response or it is sensitive to the target's water content, its orientation, its material property, its roughness. Okay, so the water content of the canopy or the foliage, the vegetation type. Why vegetation type? I mean, if you are getting response or from paddy field and forest, so both are structurally different. Both plants are structurally different. Paddy fields are more vertical, and similarly some other also. That's why the polarimetry is, I mean, the use of this has very, I mean, it is very popular in the agriculture, crop mapping, crop monitoring, this domain. Biomass, how it is calculating? Biomass, it is after all the feature, the property. Canopy structure, because polarization is sensitive to shape size. So canopy structure, it you, I mean, you can get information about the canopy structure also. So if a radar sends a pulse of vertical or horizontal polarized energy towards a group of trees, It interacts with the components present and scatters some of the energy back towards the sensors. The amount of energy received is proportional to the nature of the energy, frequency, polarization, and depends upon whether or not canopy components depolarize the signal, how far the signal penetrates, or whether it eventually interacts with the ground's soil surface. So many phenomena is happening. Also, the penetration depth and polarization. Surface, now comes the different scattering. Till now, I have mentioned the scattering, surface scattering, volume scattering, the term scattering. So, surface scattering, we'll call it the bright signals in like polarized radar image. Like polarized means HHVV. Results from single reflections from canopy components such as leaves, stem, branch, etc. So, which does not change the orientation of our transmitted signal because these are oriented horizontally, the terrain surface. When volume scattering, the energy depolarized when scattered multiple times, needle to stem to trunk within a diffused volume. So, when in which part of it will occur, of the plant or tree it will occur, when it will hit the vertical structures, and with the vertical and horizontal it will get scattered or reflected or hit multiple times. That is why we call it multiple scattering, not always volume scattering. We call it multiple scattering. This is, we already I showed this. Now we can visualize it very well. These are suppose the trees. Okay, here we have shown how it can penetrate to different wavelength bands. So before that we need to understand this is the ground, trees are vertically upward, and it has certain pattern. One very defined trunk, and the foliage is also oriented to certain directions. So it will see, or it will respond to the received signal, different parts different way. So the lowermost part that has the does not have any trees or canopy, it has only trunk and the surface. So it will show you the double bounce. Here it will hit the ground and the tree trunk only, and that is quantified by cross polarized, that is HV or VH, when your orientation is changing, transmitted signal orientation is changing. Mid of the, when there is the maximum foliage, branches, leaves, here it will just, it will see the diffuse scattering or multiple scattering. So volume scattering will happen here. And from the upper surface, surface scattering from the top of the canopy. It also depends as per, I mean, here it is said the surface and volume. It depends. Surface to some extent because it is the nearest part of the surface. Volume because multiple scatterings. It all depends on the density of the forest and the surface type also. The foliage type very much. The foliages are vertical to signal, or perpendicular to the signal or parallel to the signal. These all affects. Now when you see the L band, we already have seen L band as the higher wavelength, so it can penetrate it. Here it is shown that it is penetrating totally. No, it cannot penetrate totally till the ground for this type of forest, but it can penetrate to some extent. For C band it is halfway. For X band it will not penetrate to any that has 3 centimeter. It will just show the first. So you can see using L band we can capture all the phenomena of the scattering that is happening totally. C band we are getting only few response of the scattering, and X band it is only the upper portion of the forest. So brighter response on like polarized image, greater surface scattering, that is HHVV. Brighter response means it is sensitive to that. Response on cross polarized image, that is HVVH, it is greater volume scattering. Shorter wavelengths should be preferred while monitoring crop canopies and tree leaves, because we already studied that wavelength should be compatible or similar to our target of interest. The crop canopies or tree leaves that has very shorter size, so shorter wavelengths. Cross polarized images are less sensitive to slow variations, and same row cross planted in different directions give different response in like polarized images. To understand this, we already studied about the orientation. Orientation, I showed you the building, how it is oriented with respect to the radar movement. So same crops, that how it is planted, the orientation of the plantation, the bulk of the plantation, it will also differ. The same crop is oriented to some angle, and same crop is oriented to other angle. These two signature, volumetric signature from these two are different because the orientation matters here. So water response to microwave energy. Smooth surface of standing water reflects almost all incident radiation away from the sensor. So lower backscatter, the sensor will not get any, almost not any energy, so it will appear as darker. Turbulent surface, that is when ripples in water of water produces more backscatter because rough surface. So now the water, it is water, but because of the smooth surface, it was showing specular reflection. Now it has some roughness because of the turbulent, or because of the wind, because of the wave. Okay, so now it will act little rough compared to smooth water. Standing water under vegetation produces high backscatter. Why? Because corner reflection backscatter between surface water and stem. So when there is the only surface, soil surface and tree trunk, the response is something. And when there is the water now, so the surface gets smooth. It is not rough now like the soil surface. So it will reflect more energy now, or more the signal now. So it, because of that, it will appear brighter, or because of that, the corner reflection between surface water and stem, it will appear the brighter one, because more energy now, because of the smooth surface, it is returning. How the urban buildings are sensitive to the microwave energy. The urban buildings, cars, bridge, etc. act as corner reflectors, send much of the incident energy back to antenna, result in bright signatures for urban features. When we call it urban or urban features, what are really mean by urban features? What are the urban? This is not the building, not the cars, not the bridge only. These are the electric poles. So our polarization, that property is very much influenced by the very small structures and very these electric poles, metal structure in urban area. So all these together creates a complex environment in urban, and these two represent these type of features. We consider corner reflectors. We have studied in the first two slides corner, or about the corner reflectors. So we simulate that these type of targets with the corner reflectors, and what happens because of that, because of there the multiple scattering happens, and we get a much more energy because it is getting attenuated, you can say, by hitting the urban surfaces. Here you can see larger that this is one urban clusters area, forest, hills, mountain ridge, radar, layover, shadow we already studied, and slope here. The shadow happens here and layover, the brighter part happened here and the darker shadow happened here. We get no return from this part. City appears so bright because of what we studied just now, because of the multiple scattering from the building or city. Forest, it it is not appearing that bright, it is in the mid level, it has mixed part. So multitemporal color composites we make it like this. So we can study things like to channelize one band, date one band to red, date two to green, date three to, and this you, if you look at this, notice further the date one, this river is going, it is one. Date two, it has some dark patches. So water, these are the water. Now you can read one star image. So these are the water appeared here. And the date three, much more water or black parts are there. So what happened? This is the flood happened. Okay. So if we, I mean, channel this in RGB image, now we get this one as the flooded one. Okay. So till now I have covered the very basics of the polarization property of SAR image. And I think in any of the class someone asked about the dielectric constant and how it is influencing. So now you can understand how the higher the dielectric constant and lower, and not only because of only the material property it has dielectric constant, it the polarization property depends on the shape, size, orientation, all together are playing. So you have to, when you are collecting signature, so you have to keep in mind all those together. And if you have any questions, so geologists to study Arctic Sea. It is Arctic Sea means, I mean, what in Arctic Sea? I mean glaciers, snow. Which band they should use for snow glacier? I mean, I have already told the glacier snow, the particles are very lesser in size as compared to our building a tree. You can visualize or understand. So then obviously the lower wavelength will work. The shorter wavelength will work. But also what happens to glacier snow, the we need, I mean here the bands are not that important. Here more important is the polarization, single polarization, dual, or full, the four core polarization, because glacier, and if you, I mean consider, suppose glacier, and then I will tell about the snow. Suppose considering glacier, glacier has very smooth surface, very much smooth, and the also with that the property, the material, it is of high dielectric constant. So that to capture that polarization, we, this wavelength is secondary. We need more polarize, more bands, more channels to capture, to get all the information from the target. Similarly for snow particles, wavelength, okay, wavelength, small, shorter wavelength, and C band is always uh, medium average. So but what matters is the more the bands channels you can capture or you can get, the better, because of here, if suppose some target is, I mean sensitive to HV, but you are not getting that HV band from data, then what's the use? Okay, so to get that, it is the most important, it is dominant. Now I will um, today it is the next part of the GLCM, that is the gray level co-occurrence, the texture fixture. So texture is an important spatial property in images. There are three primary approaches to represent texture in SAR, that is statistical approach, structural approach and spectral approach. By statistical approach, we use a region histograms, their extensions and their moment as a basis. It focuses on representing the high order distribution of gray values in the image for texture representation. Structural approach, and we are least interested and we will not be covering here the structural approach and spectral approach. Spectral approach is important for in optical remote sensing. We are not dealing with the spectral curves or spectral reflectance in SAR. So, what is the GLCM? That is the full form is gray level co-occurrence matrix. So, it explores the high order distribution of gray values of pixels that are defined within a specific distance or neighborhood criterion. So the distance. So GLCM, suppose one point P with location I and J represents the distribution of occurrences of gray value pairs I and J that are separated by a distance vector D, that is dx dy. So the GLCM can be normalized by dividing each matrix value by the total number of co-occurrences, which gives the probability of occurrence for pairs of gray values separated by distance vector. So statistical structure features it is. These features are computed from the normalized GLCM, uses a second order histogram that represents the probability of occurrence for pairs of gray values that are separated by distance vector d. So this is the mathematics. We will see the application and its parameters. So it is a statistical method for examining texture by considering the spatial relationship of pixels created by calculating how often pairs of pixels with specific values and spatial relationships occur in an image. So we have to first understand what is texture. So the texture, when SAR image, it has very texture variation of texture, and the texture appears how we understand that is that has the texture. It is the variation of the lightness and darkness, high variation of lightness and darkness. So that is why it is created by calculating how often pairs of pixels that say of same value is appearing. So primary tool for text analysis in image processing applications is the GLCM. It is very popular. It is developed by scientists in 1973, and that is very much one of the most popular methods for texture analysis in SAR image. So how do we calculate? First is to choose a displacement vector, distance and direction. Second is count pixel pair occurrences for this displacement. Third one is create matrix where element represents how many times pixel value I occurs with pixel value j. Step 4, that is normalize the matrix by dividing each element by total number of pixel pairs. And common directions are 0 degree, 45, 90, 130. We'll see numericals on this. Then we'll understand more. What are the matrix, what is called by the the element and its position. So symmetry, GLCM, so key properties of GLCM is typically made symmetric by adding it to its transpose. The matrix size depends on number of gray levels in image, usually reduced to improve computation. Distance, it affects the scale of text analysis, typically 1 to 5 pixels. Direction, different directions can capture different texture patterns. Normalization converts count to probabilities, making comparisons possible. So these are the key properties of GLCM step. Now this is the most important one. When we use, suppose in software or in coding, for our application, we we can use these features or these parameters. So parameters come first, just contrast. What is contrast? It measures local variations, high for images with sharp edges. Correlation measures linear dependency of gray levels. Energy, that measures textural uniformity, high for constant images. Homogeneity measures closeness of element distribution to diagonal. And entropy, the most important one, that is the measures randomness of gray level distribution. So how to measure that mathematically? That is, it has the equations. So there are so many. I have already mentioned only few that are to our domain, to our scope. So the contrast, how we, I mean, will calculate this contrast. Correlation, how we calculate other type of correlation, cluster prominence. So these all the features today we'll also calculate in software. So better to know the theory and the concept, because we are not working, will not be working taking into consideration 20 parameters which are useful to us. We will, consider those only, and for that we need to understand the concept. Now the cluster set. What is set? I mean, these are the formula how we calculate dissimilarity, energy, entropy. So this is very important. The entropy, it is a measure of information content. Okay, it measures the randomness of intensity distribution. How random? So SAR image characteristics in GLCM in SAR image, it has the speckle noise presence requiring specialized texture analysis and high dynamic range of backscatter values. So what is the speckle noise? We have studied already the noise, clutter, speckle, and the salt and pepper effect on these. So that needs, so because of that the texture of our image, it changes. So we need to handle that. So we need special texture analysis processing to deal with the SAR image. Second is high dynamic range of backscatter values. So, there are many anomalies in SAR data. There are shadows, there are noise, and there are system interference. So, when you read the pixel numbers, DN values in SAR data, there you will see that suppose one pixel value is 5, another pixel is 5000. It can happen. So those are the anomalies, and those can be of I mean point of interest or not. That depends. But because of that, what the texture changes. The texture in the SAR image changes, and to handle that, we need this type of texture analysis. Advantages is robust to speckle noise, GLSIM, and capture spatial relationships effectively. So we are obviously working with spatial this data, what terrain and this, and it considers the spatial relationship, the distance, the orientation, and we'll see in software today that these are the weak. It these also varies with this speckle filtering. If it, the first level filtering, if we do quantization of gray levels and window size, these all will vary. So optimal window size selection, how do you select? So for high resolution SAR image, typically we'll select 7 cross 7 or 11 cross 11 this, and larger windows for lower resolution image. So that is the thumb rule. Now how to select the gray level quantization? These all options are there in software. So gray level quantization usually 16 or 32 levels for SAR image, and balance between computation cost and information retention. Displacement vector selection, we will select according to display distance, typically 1 to 2 pixel for high resolution and feature selection, contrast and homogeneity for edge detection, entropy for roughness analysis. This is very, I mean, these three that are mentioned, contrast, homogeneity, entropy, these are the popular one for GLCM texture analysis. And for when we are more into, I mean, interested into the edge portion, then we will see the contrast and homogeneity go with that. And when the roughness analysis, the randomness, the information content of the image, will look for the entropy. So these are the primary application. Again, I will skip this. So one numerical we'll see. I mean, these are just, I mean, today, I mean, we can calculate in Python, in software, in MATLAB, in 1 2 clicks, but numerical also it is very easy to do. So the matrix is given. The matrix, you can say, it represents one image of 4 cross 4 matrix. It gives, okay, I'll answer one. Let me explain this numerical first. So it creates the create GLSIM. I mean, create one GLSIM by counting horizontal neighbors. That is given. The direction is 1, theta is 0 degree. So first, what we will do, we will calculate the, I mean, normalize the GLSIM. How do we normalize? Just there is the total pairs of numbers, and we will total and we will divide those. The way we normalize. Then we calculate the energy by every each and square and addition. We'll just follow the equation or the formula. So that gives us the energy is equal to this, and this will assign to as per the weightage to our matrix every pixel. Another that is very important, contrast and homogeneity. Okay, so it how this is the matrix is given 3 cross 3 matrix. Now how to calculate contrast? The this is the given. So for each implement for 0 0, I mean, these are the position in the array or matrix. In the matrix, the 0 0 is this one. So what to do in 0 0? The direction, it is taking the direction. So 0 0, the positional, 0 minus 0 into the respective value. That way we get the contrast. Similarly for homogeneity, this is the formula, and this is how we do at 0 0 position, this 0 1 position, this, like this we will go. And so final answer, contrast, is the, we'll add all these, then we get the contrast and we get the homogeneity. We add the output and here add the output. So I think now I will show in snap the, let me show you my window. So we already processed before few data, allows 2 data and central 1 data. So today these are the, I mean, we have processed the pre-processing steps that are the important whatever you want to do. It will change little bit for polarimetry processing, but for normal processing, SAR processing, these are the, so I will, I mean, this is pre-processed and speckle filter we applied, terrain correction we did. So this we save the file, and I will simply drag this in our snap. So now we can see the, this is exported, and this is the data in Delhi. Okay. If we want to see, you can see there is the two intensity band in dB, sigma naught, that is the intensity in dB.
And we can't see. Ma'am, screen is not present.
Hello. Okay, video is not. One second. Okay, okay, sorry. I think now it's visible. So I have imported data, processed data that we processed before. And we understand, we studied all about all the pre-processing steps, what these are doing. These are the set of pre-processing for Central 1 data. For allos 2 data, there is some different. Few extra steps are here for Central 1 because this data, how it comes, how we get the signals, that is different. This is the VH band. Now we know this is the cross polarized band, VV. This is the copolarized band. Here the flood happened. Here we can see the difference. So if we want to do a GLCM texture analysis on this, we want to extract those parameters. So nothing, it is simple. We will go to raster. So now GLCM is the image analysis. That is not any connected to radar. You can do that on this. So I think that is go to image analysis, then texture analysis, then GLCM. You will click this. Now you can see here it is already input, output will take processing parameters. So which band we want to take, both bands or this, we have to select. Window size, which one to select, from 5 cross 5 to all these are available. So our data Sentinel 1 is around approx 14 cross 14 centimeter data now. So 14 cross 14 meter data. So now that for that we will use, suppose 7 cross 7. Angle, which angle to use? Suppose we are using 45. Quantizer, we already studied all this. Equal distance or probabilistic? Probabilistic is always better to do. 32 or 64. So all is no data value, it is this. Now these are the parameters we can calculate in one. So contrast, dissimility, homogeneity, all this. So I will, let's, it will take more time. Let's just deselect few. We were most generally interested. Let's just calculate all this. Then we'll see the output. Okay, meanwhile I will answer. Okay, so why entropy is important? Look, the thing is, all the parameters are important. It depends on your, I mean, task. So normally entropy, for any entropy is used. It is not in new to SAR, new to radar. It is not. Entropy is everywhere. But to know that, I mean, in terms of image, when we read image, when we process image, we look for the randomness. Okay, you might, few, if you know, I mean, if you might, I mean, mixing it with the alpha entropy eigenvalues, those decomposition in polarimetry, those also work with entropy. The main concept of entropy is same. So entropy is important because when, I mean, it basically gives you the, can say, randomness. What is meant by randomness? So suppose one value, pixel value, it is, I mean, randomly occurring at any place, and one pixel value is occurring very logically, not that randomly. It has some spatial relation. So for that, entropy will be lower, and the randomness, I mean, more the randomness, higher the entropy. Okay, and in remote sensing or in SAR, entropy, it is, I mean, you will get higher entropy when there are multiple events are happening. You, I mean, entropy is important in terms of just first to know what your, what is the information you are getting, how the information is, I mean, there, lying there, how it is arranged. So if you look at the entropy or calculate the entropy value, values of the pixels, so that will give you that how much random, or how many, you can say in terms of SAR scattering, it, I mean, captures, you can say. So more the randomness, so more the scattering it will capture. Lesser the randomness, lesser the, so it is lesser the scattering. It is not going here there. It has certain scattering types and showing. Mostly we read it that way. It is not giving you any scattering. It is not telling you that this is happening, that is happening. Entropy in terms of image, it is the randomness. Like we studied about the roughness, it the randomness. So one value, how randomly it is appearing in pixels. That is measure of the randomness. So when we see the hmm,
Ma'am, when we see the entropy, is it good to get a high entropy or a low entropy? Means, which we prefer
it
most?
is not good or bad. Okay, you can't say that it is good or bad. You, I mean, you are just getting information, and it depends on your task. And suppose building, suppose if you want to understand that way, some in one building giving you certain entropy in one image, another building giving you another, was one very higher, one very lower entropy, and these are all this contrast. Suppose you can't, I mean, identify with contrast, these are the texture parameters. So based on these you have to identify, or you have to decide that okay, these are the this, these are the that. So this is not that here, I mean, this is the good, this is the bad. It is the property of the information in your image. Okay, I mean, your information content when you are forming an image from the signal, if you want to visualize that way. So you want to know that what information, how, I mean, we plot histogram, how how our information is lying. Is there very high value, is there very low value, the range of the values, the width, the peaks, all those things. So it is like that. Entropy also like that. You can't say okay, histogram or this is good, this is bad. That is task specific. So entropy is like, it is one, you can say, feature or one parameter or one feature characteristics of the image. By that you, first of all, you can understand how your image is, how random your image is, the information in your image. Any other question? You
Okay.
can type also.
No, ma'am. Thank you, ma'am.
So we will see, you can see the randomness. I will show you. Now we calculated for two bands all these. So let's see only VH, or let's say VV1, because if we are interested in water, that is the VV surface. So now suppose first take the VV intensity entropy. See, so it has the higher value for this portion and lower value this. So higher value in entropy. What does it mean? It is that much random, and lower value low I mean, less random in the this values. So what does it mean more random? What does it mean less random in our image or in SAR? Because you can read it that way. If you see the original image, this is okay. But here so many values are lying in so many scale. So many scattering are happening. Okay. Physically you have to understand this way. So many scattering are happening this way. But when in water, suppose only specular or only surface scattering is happening here. So that is not random. That has some direction. Because of that, the randomness is so less here, and that's why the entropy here also lesser. And like that the patches here. Here you can see the cities. The patches, dark patches are cities. These are here now, it is not any scattering, nothing, not any intensity, not any brightness. Here we are reading an entropy image. Entropy that way that here building shows the double bounce. It hits twice. So we call it double bounce. So there mostly buildings are showing that type of scattering. So that has some range of values that is given. That is not random. One building is not random to another, and so that is why this. But where these are the highly random, okay, these are the portions that are the highly random features that are these places. So it also depends on many, because few are like here the built up, and here see, so this is how you study the entropy, and we will see measure the homogeneity, or suppose let's see the contrast. It is the same way. So which is the dominate, which dominates more? It's the contrast one. Dissimilarity, so we get all different things. Homogeneity, now these three are very important: GLC, mean, variance, and correlation. Okay, so correlation, it is giving you not that so highly correlated, you can say. Okay, this appears so bright that almost white, so it is highly correlated, the nearby pixels. So this is the way we we can calculate for our very basic processing the GLSM parameters. And how to use this after this, we can suppose we want to work with homogeneity software. So we will just right click on the image, export view as image, see the full scene. Okay, and we select the geotiff, and suppose we will select the this, and we will export the geotiff image, the whole the tile. We already calculated this. And if we want, suppose this is our file homogeneity, suppose let's move this here, this is the homogeneity, and think in QGIS, let's show you. So we got this parameter image, this is the geotiff, and these are the intensity only. Okay, you can't process the polarimetric processing, or can't process extract the parameters from intensity, because it needs intensity and phase both, because phase is the orientation, and polarization polarimetry relates to orientation. If orientation is not there, nothing is there. So if phase is not there, nothing. So normally we use intensity only, but when polarimetry comes, then we use intensity and phase both. So these GLCM, these are the intensity based texture analysis. If we just export this, now we can see it is geocoded. It has the reference, all the bands came, and it has this mean, max, standard deviation, all these things. You can read it by this way. And this is now, if you want to suppose study homogeneity for this portion flood part, you will take subset of this or so on. And this is the resolution for this is, when Sentinel 1 when multi-look, it gives you approx 14.6 square pixels. So now you can resample this accordingly and use. And if you want to so suppose this is the way we actually, this is the color map we present the homogeneity or any SAR image. Okay, these are the more to understand. Now if we the transparency of it, you can visualize this way. So this is the Jamuna river going, and the flood happened, and to nearby areas also, how it is lying on. So it is very easy to do with the snap software, and we can extract the GLCM parameters and text analysis, and can do our classification further and all those taking multiple parameters. So this only hands on for today. Rest, I think. If anyone has any question, you can type. So till now today, this is it. And majorly for polarization, from basics to very advanced, you always can refer these last two types of two books. This Skolnick is much more electronic side, mathematical. You will get the mathematical background. This is more remote sensing based, and you will get basics of the polarimetry. And if anyone has any question, you can ask, you can type, you can ask anything, any application based anything, any question or anything you want me to include in our next slides next week, or if you want me to repeat anything in more detail, because next week also I think I will be covering the polarimetry some more and also some other topics. So if you want me to tell or discuss any topic in detail, then I can discuss that next week also. And today if you have any question, you can tell me. So I have not. Okay, but I think you should. Initially in my classes I used to discuss assignments, MCQs. That now, I mean, not much response I get. That's why I stopped that. But that are very useful for to revise every class, and finally that you will remember only that, and that makes your concept clear. Not like studying the theory only. The practical, the application oriented, you need the concept, and that will come only with the assignment. If you don't have any question, then it is difficult. It is better to have any question, any query, any information, anything. You can also mail me here. I said this before also. So we have seen the Sentinel-1 C-band today in Snap software, the C-band processing of GLCM texture, and we have the allosh 2 data also, that I think we will see next class, or maybe today also I can show. It will be completed, and you can get to see that how it is differing from the C band. So allosh 2 has L band. So now we already processed before the allosh 2 data, pre-processed. So this is our pre-processed data. We will simply import that, and allows to data we have, it is the quad pole data. Okay, this is the commercial data we have purchased, and now you can see the intensity and it is the quad pole. The 4 bands are there. Here we only got, it is the open source data Sentinel-1. Here it is the quad pole. So we can see here, suppose the VV. This is the VV band, and this has the, we can further process this. Now let's just calculate these two with the same window size, though it should not be the same because allows to, this is high resolution. Let's run this. It is getting so much time because I think we have processed all the 4 bands. So let's just cancel this. Let's process only one band, the PV band. Let's select plus 7. So the processing is done. We will see the homogeneity and the entropy. Similarly, you can see the entropy here. For here, randomness is so low, it is defined, and these are the some of the built-ups, buildings and agriculture. Not much building. This is mostly vegetation and water and hill. So here, not much response like this. So you'll get some higher entropy for here also. So I think we have seen the allows 2 application. So for today I think that's it. Next week I'll be covering whatever the next syllabus will get, and if you have any question you can mail me any queries. Okay, thank you for today.